Hi, welcome back to my class in number 3. For today, we will discuss the Euclidean algorithm. The Euclidean algorithm, unlike the division algorithm, is actually an algorithm for finding the greatest common divisor between two integers a and b. But there is a condition that must be satisfied by these two integers a and b. In applying the Euclidean algorithm, the problem is to find the greatest common divisor of a and b. A and b are integers. And this is the inequality or condition that must be satisfied by the integers a and b. A is greater than equal to b and b is greater than equal to 0. This inequality implies that b is a positive integer or zero integer. And by transitive property of inequality, if a is greater than equal to b and b is greater than equal to 0, then that implies that a is greater than equal to 0, which means that a is also a positive integer or is equal to 0. In the last lesson, we defined the greatest common divisor of two integers. By definition of greatest common divisor of integers a and b, the greatest common divisor of integers a and b is the largest positive integer. The largest integer that can divide both a and b. And last time we also defined the set of all divisors of integers a and b denoted by capital C of ab. Capital C of AB, C of AB is the set of all divisors, common divisors of the integers A and B. And the largest element of this set of all common divisors of A and B is the greatest common divisor of the integers A and B. And we actually write GCD of AB equals the maximum of the elements of C, the set of all common divisors of AB. Last time we defined briefly the greatest common divisor of A and B as the maximum among the maximum element among the elements of C of AB, the set of all common divisors of AB. So if GCD of AB equals the maximum of this set, then the greatest common divisor of A and B is the largest integer that divides A and B. And by our definition of divisibility, if D is a common divisor of A and B, then B divides A and D divides B. Again, if D is a common divisor of A and B, that means D is an element of C of AB, the set of all common divisors of AB, then D divides A and D divides B. And we will use some of the properties of divisibility later on when we find the greatest common divisor of the positive integers A and B that satisfy this inequality, A greater than equal to B and b greater than equal to 0. We start with b equals 0, but a is greater than 0. If b is equal to 0 and a is greater than 0, then a is greater than b, because b is 0 and a is greater than 0. And for this value of b and for a positive integer a greater than 0, we find the greatest common divisor of ab, and this simplifies to greatest common divisor of a and 0. Again, if b is 0 and a is a positive integer greater than 0, we find the greatest common divisor of ab. A is greater than 0 and b is equal to 0. So we actually find the greatest common divisor of a and 0. We let C of A0 be the set of all common divisors of A and 0. Now consider 0. Um, every integer, one of the properties of divisibility is that every integer divides 0, including 0. 0 divides 0. But not all the divisors of 0 can divide a, which is greater than 0, not equal to 0. A is not equal to 0, but greater than 0. Again, every integer divides 0, including itself. 0 divides 0 because one of the properties of divisibility says that everything divides itself. That is, if n is an integer, then n divides n. So 0 divides 0. And another property of divisibility, every integer divides 0. But not every integer can divide a non-zero integer, but a positive integer. Example, 0 divides 0, but 0 does not divide a. 0 divides a only if a is equal to 0. And that's another property of divisibility. But all the divisors of a, which are integers, including a, can divide 0. The divisors of a are integers. And all the divisors of a can divide 0 because every integer can divide 0. Therefore, this set of common divisors of a and 0 is actually the set of divisors of a. Now, we know that the set of all common divisors of A and 0 is the set of all divisors of A. And from this set, C of A0, we will find the maximum of the element of C of A0, the largest element of all the common divisors of A and 0, or the largest element of the set of all divisors of A. Now, from last time, we have also shown that if A is a positive integer, then the largest number that can divide A is the absolute value of A. Please refer to your notes for the proof of that. If A is greater than 0, then the largest number, the largest integer that can divide A is the absolute value of A. Now, we know that the common divisors of A and 0 are the divisors of A. And based from this statement that says if A is greater than 0, then the largest integer that divides A is the absolute value of A. And if C of A is the set of all divisors of A, which includes A itself, then the largest integer that divides A is the absolute value of A. Therefore, we conclude that the greatest common divisor of A and 0, which is equal to the maximum of the elements of C of A0, is equal to the absolute value of A. Again, the set of all common divisors of A and 0 is the set of integers that divide A. And that includes, this set C of A0 includes A itself. And by this statement, if A is positive, we have shown last time that the largest integer that divides A is the absolute value of A. The largest integer that divides A, which is this set C of A0, is the absolute value of A. And therefore, the absolute value of A is the greatest common divisor of A0. But if A is greater than 0, then the absolute value of A is A. This means that the absolute value of a positive integer is itself. We are given that A is greater than 0, then the absolute value of A, which is greater than 0 positive, is equal to itself. Therefore, the greatest common divisor of A0, if A is greater than 0, is equal to absolute value of A, and absolute value of A is equal to A. We therefore conclude that the greatest common divisor of A0, if A is positive, is equal to A. Hence, we have found the greatest common divisor of AB for the case where B equals 0 and A greater than 0. And this greatest common divisor of AB simplifies to greatest common divisor of A0. And the greatest common divisor of A0 we have shown is equal to A. If A, this applies only if A is greater than 0. And A should be greater than 0 by this requirement of the Euclidean algorithm. We now consider the second case. Now consider case 2 as another set of values for A and B. But in case 2, we let both A and B be equal to 0. If A is 0 and B is 0, this inequality is satisfied. A equals 0 and 0 equals 0. And for these values of A and B, we find the greatest common divisor of AB. If A and B are both 0, then the greatest common divisor of AB simplifies to the greatest common divisor of 0 and 0. Now, I have defined this in the lesson before this lesson, but again, every integer divides 0, including 0 itself. And the same here, every integer divides 0, including 0 itself. Therefore, the common divisors of 0 and 0 is the set of all integers. But the set of these integers has no largest element because the set of integers is an infinite set. That is, there is no largest element. And so, last time we defined the greatest common divisor of 0 and 0 as 0. Therefore, the greatest common divisor of 0, 0 equals 0. Now, we consider the case where we consider this case where A equals 0. But B is greater than 0, which means B is a positive integer and A is the 0 integer. For these values of A, B, we check if the inequality is satisfied. A is 0 and 0 is not greater than B because B is greater than 0. And if A is 0, 0 is not equal to B because B is not 0 because B is greater than 0. Therefore, these values of A and B, where A is 0 and B is greater than 0, is not a possible case. So we cannot find by Euclidean algorithm the greatest common divisor of AB if A is 0 and B is greater than 0. Actually, the Euclidean algorithm applies only for finding the greatest common divisor of AB where A is greater than B and B is greater than 0. Or A and B are equal, both positive and equal, or they are equal but both are equal to 0. And the Euclidean algorithm does not apply for this case where A is equal to 0 and B is greater than 0. Because this inequality A greater than equal to 0, A greater than equal to B is not satisfied by these values of A and B. So we consider the last case where A and B are both greater than 0. for these values of A and B that are both positive and non-zero, we find the greatest common divisor of AB. Suppose we write A as, by division algorithm, we write A as B times Q plus A remainder. We write A as a multiple of B plus a positive remainder R. And if we write A in this form, we will show that the greatest common divisor of AB is equal to the greatest common divisor of B and the remainder R. Now we let D as one of the common divisors of A and B. We take an arbitrary element of CAB, the set of all common divisors of AB, and we denote this by D. So D is any integer that is a common divisor of A and B. If D is a divisor of A and B, then D divides A and D divides B. By definition of divisor, or if D divides is a common divisor of AB, then we conclude that D divides A exactly, and also D divides B exactly. And from this equation, we solve for R, and we will show that D also divides R. If D divides A and B, then D also divides R. We solve for R from this equation by transposing BQ to the left-hand side. Therefore, R is equal to A minus BQ. Transpose BQ to the left-hand side, you get A minus BQ equals R, or R is equal to A minus BQ. because we have written R as A minus BQ, this expression represents a linear one of the linear combination of the integers A and B, where the numerical coefficient of A is 1 and the numerical coefficient of B is minus Q. So A minus BQ is a linear combination of the integers A and B. And there is a property which we have taken before, the linearity property of divisibility. If D divides A and D divides B, then D also divides the linear combination of A and B. And such linear combination is this A minus BQ. Thus, by linearity property of divisibility, we say that D divides A minus BQ, which is a linear combination of AB. And from this, we conclude that D divides R, where R is A minus BQ. R equals A minus BQ. So here we have D divides B and D divides R. That means that D is one of the elements in the set of common divisors of B and R. If D divides B and D divides R, then D is also an element of the set of common divisors of B and R. The element we conclude from here, D divides B and D divides R. We conclude that D divides B and R, which means that D is one of the elements of the set C of BR, the set of all common divisors of B and R. But here we suppose that D is any arbitrary element of C of AB. That means D is any common divisor of AB. So any common divisor of AB is also a divisor of BR. Now we will show that if we take an arbitrary element of this set that divides BR, that element also divides AB. And if we can do that, we will conclude that the set of common divisors of AB is equal to the set of common divisors of BR. To be consistent with our notation, we take the same letter, the same notation D to represent any arbitrary element of the set of common divisors of B and R. If this element of this C, set C of BR, that means D is a common divisor of B and R, then D divides B and D divides R. But we suppose that we let that A is equal to BQ plus R. Again, we apply the linearity property of divisibility that says if D divides B and D divides R, Then, by linearity property of divisibility, D also divides the linear combination of B and R. And such linear combination is given by this expression, by this sum BQ plus R. This sum represents one of the many possible linear combinations of B and R. So if by linearity property of divisibility, if D divides B and D divides R, therefore D divides BQ plus R, because this is a linear combination of B and R. But BQ plus R is equal to A. Therefore, D divides A. Again, we let A equals BQ plus R, which means that B and R, the sum BQ plus R represents a linear combination of BR. And by linearity property of divisibility, if D divides B and D divides R, the linear combination of B and R is also divisible by D. That means D also divides the linear combination of BR. And BQ plus R is one of the linear combinations of BQ. Therefore, by linearity property, we say that D divides BQ plus R, a linear combination of B and R. But BQ plus R is equal to A, thus D divides A, where A equals BQ plus R. Now we have here D divides A and D divides B. If D divides A and D divides B, we therefore conclude that D is one of the elements of the set C of AB, the set of all common divisors of AB. Now, we have shown that if D is any arbitrary element of the set C of AB, D is any of the common divisors of AB, this D element of CAB, we have shown, is also an element of the set of all common divisors of BR. And if we take any arbitrary element of C of BR, that is D is any common divisor of BR, we have shown that this D, element of the set of common divisors of BR, is also an element of the set of common divisors of AB. So if D is element of CAB, D is element of CBR, and vice versa. If D is element of CBR, we have shown that D is also element of CAB. And combining these two results, we conclude that the set of all common divisors of AB is the same set, is equal to the set of common divisors of BR. Again, combining the two results we obtained, we conclude that the set CAB, the set of all common divisors of AB, is equal to the set CBR, the set of all common divisors of BR. Now, if these two sets are equal, the maximum of this set must be equal to the maximum element of this set. So, the equality of these two sets implies that maximum, the largest element of the set of all common divisors of AB, is equal to the maximum of CBR, the largest element of the set of common divisors of BR. And this largest element of these common divisors of AB is defined as the greatest common divisor of AB. And it should be equal to and is equal to this maximum of CBR is the largest element of the set of all common divisors of BR and is defined as the greatest common divisor of BR. Therefore, we have found that if A is positive, greater than 0, and B is greater than 0, the greatest common divisor of AB is equal to the greatest common divisor of the integer B and the remainder R. If we write A as BQ, B times some integer, if we write A as BQ plus R, where Q is some positive integer and R is a positive remainder. Now, the process we have used for finding the greatest common divisor of AB being equal to the greatest common divisor of BR in case 3 where A is greater than 0 and B is greater than 0, but A is greater than B is applied repeatedly, and this process constitutes what is known as the Euclidean algorithm. We now apply the Euclidean algorithm to find the greatest common divisor of the following sets, following pairs of positive integers. Number 1, we find the greatest common divisor of the integers 40 and 24. And we apply the Euclidean algorithm in this problem. A is 40 and B is 24. And apply our findings in case 3. The greatest common divisor of AB is equal to the greatest common divisor of BR. The greatest common divisor of 40 and 24 by this result is equal to greatest common divisor of B. B is 24. And the integer R, the remainder, if we write 40A as B multiplied by Q, which is some positive integer, plus the remainder. Now, you think of a positive integer when you multiply by 24, the product is not more than 40. And if we try 2, you multiply 24 by 2, 24 multiplied by 2, that's 48. And 48 is more than 40. So we take 1. Our Q is 1. 24 multiplied by 1 is 24, and that's less than 40. Now we should add an integer here, and that would be our remainder, so that the equality remains true. And the remainder here is obtained by subtracting 24 multiplied by 1 from 40, or 40 minus 24 times 1, or 40 minus 24 is equal to 16. Now this is the form A equals B times Q plus R. Therefore, our R in this notation is 16, the remainder. And we again apply this process or this finding to the greatest common divisor of 24 and 16. Where we now take A, 24 as A, and 16 as B. And by this finding, the greatest common divisor of 24 and 16 is equal to the greatest common divisor of B, which is now 16. And R, the remainder, if we write 24, 24 is A as B, 16, multiplied by a positive integer plus a remainder R, also a positive integer. Again, you think of a positive integer. When you multiply by 16, the product is not more than 24. Suppose we try 2, 16 multiplied by 2 is 32, and 32 is more than 24. Now we cannot have 32 because our remainder would be negative. And in the division algorithm, the remainder is positive. So the integer here to be multiplied by 16 should be 1. And we should add a constant here, an integer, and that is our remainder to maintain the equality. And the number to be added here is the difference between 24 and 16 times 1. Or 24 minus 16 times 1 equals 24 minus 16 equals 8. Now this is of the form A, 24 equals B, 16 times Q, Q is 1, plus R. Therefore, R is equal to 8. Again, we apply these findings to the greatest common divisor of 16 and 8. We find a greatest common divisor of 8 and a remainder R. For the greatest common divisor of 16 and 8, A now is 16 and 8 is your B. And by these findings, the greatest common divisor of 16 and 8 is equal to greatest common divisor of B. B now is 8. And we find the remainder R by writing 16 A as equal to B, 8, multiplied by an integer Q plus a positive integer which we take as R, the remainder. Now you think of a positive integer. When you multiply by 8, the product is either less than 16 or exactly equal to 16. The product should not be more than 16. Now suppose we try 2. If you multiply 2 by 8, you get 16, and that product is exactly equal to a 16. So we can take Q equals 2. Always take the largest integer. When you multiply that integer by B, the product is less than or equal to A. Now, what integer should be added here so that the equality remains true? Again, we subtract 8 times 2 from 16, or 16 minus 8 times 2. That's 16 minus 16, 0. So we add 0 here. Now this equation is of the form A 16 equals B 8 multiplied by Q2 plus R now is 0. Hence the greatest common divisor of 16 and 8 equals greatest common divisor of B 8 and R 0. Now we find the greatest common divisor of 8 and 0. In case 1, we have shown that if B is 0 and A is greater than 0, then the greatest common divisor of A0 is A. Now that is in this form, greatest common divisor of 8, 0, where A now is 8. So applying that result earlier that we obtained, greatest common divisor of A0 is A, where A now is 8. Thus, the greatest common divisor of 8 and 0 is 8. And the final answer, the greatest common divisor of 40 and 24 is 8. Because this is equal to this, and this is equal to this, and this is equal to this. And greatest common divisor of 8, 0 is equal to 8. Therefore, the greatest common divisor of 40 and 24 is 8. That is, the largest positive integer that can divide 40 and 24 is 8. And that's the greatest common divisor of 40 and 24 equals 8, obtained by Euclidean algorithm. We take another example. For our example 2, we find the greatest common divisor of the integers 72 and 18. In this example, A now is 72 and B is 18. Again, the condition for application of Euclidean algorithm is satisfied. A must be greater than B. A 72 greater than 18 B. And by the result we obtained earlier, the greatest common divisor of 72 and 18 is equal to the greatest common divisor of B, 18. And a remainder, if we write 72 as A equals B, 18, multiplied by some positive integer plus a positive integer, which we take as the remainder R. Now you think of the largest positive integer such that when you multiply it by 18, the product is either exactly equal to 72 or less than 72. Suppose we try 4, 18 multiplied by 4 is 72. Multiplied by 4, 32, carry 3, 72. Exactly 72. So the constant to be added here is 72 minus 18 times 4, or 72 minus 72, 0. This equation is of the form A equals B times Q plus R. Therefore, R is 0. And the greatest common divisor of 72 and 18 equals the greatest common divisor of B, 18, and R, 0. And now we find the greatest common divisor of the right-hand side of 18 and 0. and applying the result we obtained earlier, that the greatest common divisor of A and 0, where A is greater than 0, is equal to A. A here is 18, therefore the greatest common divisor of 18 and 0 is 18. Now, greatest common divisor of 72 and 18 is equal to the greatest common divisor of 18 and 0, which is equal to 18. Therefore, we write the greatest common divisor of 72 and 18 is 18. 18 is the largest positive integer that can divide 72 and 18. We now take another example. We find the greatest common divisor of the positive integers 180 and 132. In this example, A is 180 and B is 132. You can see that A, 180 is greater than B, 132. Therefore, we can apply the Euclidean algorithm to find the greatest common divisors of 180 and 132. And by the result we obtained earlier, the greatest common divisor of AB is equal to the greatest common divisor of B, which is 132, and the remainder R. And we find the remainder R to be written here by writing A, 180, as B, 132. Multiplied by some positive integer denoted by Q, plus a positive integer denoted by R, which we take as the remainder R here. Now think of the largest positive integer such that when you multiply that largest positive integer by 132, the product is either exactly equal to 180 or less than 180. And we cannot use 2 or greater than 2. Suppose you try 2, you will get 132 multiplied by 2, you get 264, and 264 is greater than 180. So we take 1 as the positive integer Q and multiply that by 132. The product 132 is less than 180. And we should add a constant here to be taken as R, the remainder, by subtracting 132 times 1 from 180, or 180 minus 132 times 1, or 180 minus 132, you get 180 minus 132, 48, plus 48. Now, this equation is of the form A equals BQ plus R. Therefore, R is 48. And the greatest common divisor of 180 and 132 equals the greatest common divisor of B, 132, and the remainder R, which is equal to 48. Now, we find the greatest common divisor of 132 and 48. Our A now is 132, our B is 48, and by the results we obtained earlier, the greatest common divisor of AB is equal to greatest common divisor of B. B now is 48. And the remainder R. which we obtained when we write 132a as equal to b 48 multiplied by some positive integer plus some positive integer which we take as r, or the remainder. Now, think of the largest positive integer such that when you multiply it by 48, the product is exactly equal to 132 or less than 132. Suppose we take 2, 48 multiplied by 2, you get 16, 1, 8, 96. 96 is less than 132. Suppose we try 3. 48 multiplied by 3. 3 by 8 is 24. Carry 2. 3 by 4 is 12 plus 2 is 14. If we take Q equals 3, 48 times 3 is 144. And 144 is greater than 132. Therefore, 3 is not possible. And we take now Q as 2. If 2 is multiplied by 48, 96 is less than 132. Therefore, our final Q is 2. 2 is the largest integer, the largest positive integer. When multiplied by 48, the product is less than 132. And we must add a constant here to be taken as r, or the remainder, by subtracting 48 times 2, which is 96, from 132. Or 132 minus 48 times 2, or 132 minus 96. 132 minus 96 equals 36. So the constant to be added here is 36 to maintain the equality. This is now of the form A equals B times Q plus R. Therefore, R equals 36. Now we find the greatest common divisor of 48 and 36. We now take 48 as A and 36 as B, and by the result earlier, the greatest common divisor of A, B is equal to greatest common divisor of B, R, where B is 36. And R we find by writing A, 48, as equal to B, 36, multiplied by positive integer Q, denoted by Q, plus a constant denoted by R, known as the remainder. Now we think of the greatest positive integer. When you multiply it by 36, the product is less than or exactly equal to 48. If we multiply 36 by 2, that's 72, and 72 is greater than 48. So we cannot take 2, we take 1 multiplied by 36. 36 is less than 48. And we must add a constant here to keep the equality sign. And the constant to be added is obtained by getting the difference between 48 and 36 times 1, or 48 minus 36 times 1, or 48 minus 36 equals 12. This is now of the form A equals B times Q plus R. Therefore, R is 12. Now we find an equal number for the greatest common divisor of 36 and 12. Where 36 now is taken as A and 12 now is taken as B. And by the result earlier, the greatest common divisor of A is greater than B, 36 is greater than 12, is equal to greatest common divisor of B, 12, and a positive integer R, which is the remainder when we write 36 is equal to B12 multiplied by some positive integer denoted by Q plus a constant denoted by R. Now we think of the largest positive integer. When you multiply it by 12, the product is exactly equal to 36 or less than 36. And we try 3. 12 multiplied by 3 is 36, and the product is exactly equal to 36. Therefore, 3 is the largest integer, such that when you multiply it by 12, the product is exactly equal to 36. And the number, the integer to be added here is the difference between 36 and 12 times 3, which is also 36. 36 minus 36 is 0. Therefore, this is A equals B times Q plus R. Therefore, R equals 0. So the greatest common divisor of 36 and 12 equals the greatest common divisor of 12 and 0. Finally, so by now you can now see the pattern. You stop, and the algorithm ends when you reach the point when you get the greatest common divisor of a positive integer and 0, which is equal to the positive integer, denoted by A. And by using the result we have earlier, the greatest common divisor of A and 0, where A is greater than 0, is equal to A. Where in this example, A now is 12, so the greatest common divisor of 12 and 0 is 12. And 12 is the greatest common divisor of 180 and 132. 12 is the largest positive integer that can divide 180 and 132. And we now take a last example. For our last example, we find the greatest common divisor of the integers 1035 and 621. In this problem, A is 1035 and B is 621. And by the results we obtained earlier, the greatest common divisor of integers A and B, where A is greater than B, is equal to the greatest common divisor of B, 621, and R. Denoted R, the remainder R, which we will now find. And we find the remainder R by writing A, 1035 as equal to B, 621 times a positive integer Q, plus a constant which we take as R. Now we think of the largest positive integer such that when we multiply it by 621, the product is not more than 1035. Suppose we try 2 and the product would of 2 and 621 would be 1242, which is greater than 1035. Therefore, we take the positive integer here as 1. 1 times 621 is 621 and it's less than 1035. And we must add a constant here to maintain the equality. And that constant to be added here is the difference between 1035 and 621 times 1, or 1035 minus 621. And the difference of 1035 and 621 is 414. Therefore, the remainder R that we are looking for is 414. Now we write an integer that is equal to the greatest common divisor of 621 and 414. For this, A now is 621 and B is 414. And by the results we obtained earlier, the greatest common divisor of 621 and 414 is equal to greatest common divisor of 414. And a positive integer called the remainder, obtained when we write 621a as equal to b 414 multiplied by some positive integer denoted by q plus a constant denoted by r. And we think of the largest positive integer when we multiply by 414. The product is not more than 621. And we cannot use 2 here because 2 multiplied by 414 is more than 621. Therefore, the integer here is 1. Should be 1. 1 multiplied by 414 is 414 and it's less than 621. The constant to be added here is the difference between 621 and the product of 414 and 1, or 621 minus 414. (621 minus 414 is 207. This equation is now of the form A equals B times Q plus R. Therefore, R is 207. Now, we find the greatest common divisor of 414 and 207. Where A now is 414 and B is 207. And this greatest common divisor of 414 and 207 equals greatest common divisor of 207 and a positive integer denoted by R. And we find the positive integer here denoted by r by writing A414 as B207 multiplied by some positive integer denoted by Q plus a constant denoted by R. And we think of the largest positive integer such that when we multiply it by 207, the product is either exactly equal to 414 or less than 414. Suppose we try 207 multiplied by 2 is 414, and it's exactly equal to 414. And the constant to be added here is the difference between 414 and the product of 207 and 2. We have 414 minus 207 times 2, or 414 minus 414 is 0. Therefore, the remainder R is 0. And finally, we have the greatest common divisor of an integer a, which is 207, and 0, which we have shown earlier is equal to a if a is greater than 0, like 207 greater than 0. Hence, applying the property, the greatest common divisor of a and 0, where a is greater than 0, is equal to a. The greatest common divisor of 207 and 0, where a now is 207, is equal to a, 207. Therefore, we conclude the greatest common divisor of 1035 and 621 is 207. Or the largest positive integer that can divide exactly 1035 and 621 is 207. And you can check your answer. You divide 1035 by 207, the remainder must be 0. Also, if you divide 621 by 207, the remainder must be 0, which means that 135 and 621 are exactly divisible by 207, and 207 is the largest positive integer that can divide 1035 and 621. And we call 207 as the greatest common divisor of 1035 and 621. For your exercise, please try the following problems. Find the greatest common divisor of 56 and 21. Number 2, greatest common divisor of 154 and 42. 3, greatest common divisor of 108 and 60. 4, find the greatest common divisor of 230 and 184. And 5, find the greatest common divisor of 2,240 and 1,056. In all of these problems, you apply the Euclidean algorithm, the process we have used in our examples. And that completes our lesson for today on Euclidean algorithm. The method for finding the greatest common divisors of two integers a and b, where a is greater than or equal to b and b greater than equal to 0. If you have question about the lesson today, you ask your question in the comments below. Thank you for joining me in my class today in number theory.